Now that we have some familiarity with the properties of light and wave-like phenomena, we're now going to turn our attention to the quantum mechanical behavior of light. To set the stage for this exploration, we're going to explore two related concepts that are directly related to wave-like behavior, namely diffraction and interference. So first up, diffraction is a process in which a wave, when it encounters either an obstacle or a slit that is comparable in size to its wavelength, there is a resulting bending process that occurs, right? And so illustrated here below, we see a wave coming in, traveling in this direction, encountering a slit whose width is on par with the wavelength of the incoming waves, and we say that as this wave impacts that slit, you're effectively forming a new wavefront that's bent around that opening. Now, of course, this is a very distinctly wave-like process. If we compare this behavior to what we would expect if we had, say, particles being, thrown or projected towards this slit, you basically have a situation where that particle beam, if it's coming in exactly perpendicular, to the wall with the slit in it, you're either going to have that beam impacting the wall or the particle being able to pass directly through. Of course, in practice, you could get a few of them bouncing off the edges, if you're coming in at a slightly different angle. But suffice it to say, you're not going to be seeing this bending occurring. We see everything traveling in a straight line in the case of particles. So this is the first distinction we want to make here. Wave behavior is very much characteristic of this, or this diffraction pattern is very much a characteristic of this wave-like behavior, and the particle behavior is what we'd observe if there's no bending. Okay, now interference is our second wave-like behavior that we're going to discuss here. And so interference is probably best illustrated in the following example. Let's suppose that we have an incoming wave, and that incoming wave is going to be impacting on a wall that has two slits. And both of these slits are once again, openings that have a diameter that's on par with the wavelength of that incoming wave. So we saw in the previous section that each one of these slits, right, is going to result in diffraction of this wave. So we're going to see a bending, essentially a new wavefront forming at this position of the first slit, and then the same thing is going to happen at the position of the second slit. So what we effectively have is two new wavefronts coming out of each one of these slits, right? And they're both being formed from this initial incoming wave, okay? So here's the interesting part. Because we now have two wavefronts, right? After we've impacted, we've essentially gone through this barrier with the two slits, this double slit setup, we are going to have the opportunity for these waves to interact with one another, right? And there's effectively two types of interactions that we really care about here, right? These waves could interact in a way such that when this S1 wave is at its high point, it's going to overlap with the high point of this S2 wave, right? If that happens, we're going to have a situation illustrated right here on the left-hand side, right? So the high point of the S1 is lining up with the high point of the S2 wave, and the result is that both of these waves are effectively going to add together. And this sort of interference is what we call constructive interference, right? So you're constructing an even larger wave, right? Now, the opposite of this is, of course, a situation where the low point of the first S1 wave is directly interacting with the high point of the S2 wave. In this case, if we sum up the negative and positive here, where they're actually going to effectively cancel each other out. And you can kind of follow that along as you trace out these two wave patterns. If you take just the mathematical sum of these two waveforms, you actually get nothing, right? And so this would be complete destructive interference. So these are the two extremes, right? perfect constructive interference on the left, perfect destructive interference on the right, and of course, depending on the overlap of these waves, you can get something in between. So if we ask the question then what this looks like, right? If we go over to the right-hand side after that wave has passed through that double slit, you end up with a picture that looks something like this. You're going to have regions where constructive interference is occurring. And so those are illustrated by these blue lines here. Right? And so we're talking about light, so that basically is going to manifest on the viewing screen on the far end of the double slit as a white portion or a bright portion. All right? Then adjacent to every one of those bright portions is going to be a portion where you're going to have destructive interference, illustrated right here. And that's, of course, is going to be a situation where the light, the two wave fronts of the light at the first slit and second slit effectively cancel each other out, destructive interference, and you're going to get a dark spot, right? And you can do some calculations, and you can basically, depending on, the separation distance between these two slits and the wavelength of the light, you can actually predict where you're going to see these regions of destructive, constructive, destructive, constructive, destructive, and so on and so forth, interference showing up. And so the fact that if you take a light source and you shine that light source at a double slit setup and you look at the resulting pattern on the far end, you see this diffraction pattern, you see this interference pattern where you have both constructive and destructive interference occurring. And so the result then of this experiment is basically that light is in fact behaving as a wave in this experiment. So the so-called double slit experiment tells us that light is behaving as a wave. Okay, so now we're going to turn our attention to the first experiment that really started to draw out some of this strange quantum mechanical behavior of light. And it's really going to pave the way for an understanding of strange quantum mechanical behavior across the board. And so this experiment is called the photoelectric effect. Illustrated here is the experimental setup that allows us to explore and understand the so-called photoelectric effect. So the heart of our experimental setup here is an evacuated chamber, and inside that evacuated chamber is a piece of metal. Okay, and so remember, evacuated chamber basically means we've taken out as many as we can of air molecules in the air, and so basically think vacuum. So you've got a little vacuum chamber in here, and you've got a piece of metal, and then you've got another little positive terminal, another little electrode sitting in right here. Okay. So basically what happens is, if we put a certain type of light, and we'll talk more about that later, but if you have a certain type of light coming in through this transparent cover of the evacuated chamber, and that light impacts that metal surface, then under certain circumstances, what happens is electrons end up getting ejected or kicked out of that metal. And remember, electrons are negatively charged, so if we've now introduced a moving charged particle, right, we can basically form an electrical current. And so if we set this whole setup in a circuit with a battery and a meter that allows us to measure current, then what we can effectively do is monitor for when electrons are kicked out. If an electron's kicked out, then you have charges that can move, you can complete this circuit, and you're going to see a current. Now, this observation in and of itself wasn't particularly alarming, right? And in fact, with this wave-based notion, this wave-based explanation of what light is, we basically come up with a sort of prediction where the mechanism of action is basically an energy transfer process where that incoming light is transferring energy into that metal, and if there's a sufficient amount of energy, that electron is then kicked out and you get that current. Okay, so now the prediction of a sort of wave-based explanation of what light is would then say that, well, what would happen if we were to put more and more light into that metal sample? So we've got our little piece of metal sitting here, right? Rather than having one incoming, light wave, put a bunch more in there, right? Well, we would predict that the more light that we put into our system, right, the more electrons that are going to be kicked out, which of course would correspond to an increase in current. So more light, we're basically saying increase our intensity. Okay, increase the intensity, more light hitting the metal, more electrons coming out, more current. Seems simple enough. But of course, here's where the problem comes in. It turns out that this wave-base prediction of what would happen in this photoelectric effect experimental setup is incorrect entirely. So this plot down here, I want to take a minute to make sure we understand what's happening. So what I'm plotting along the horizontal axis here is frequency of light. So remember, the speed of light is related to the wavelength of frequency using this relationship down here. So we can talk about wavelength of light or frequency of light and obviously go back and forth between the two. And we remember that the frequency of light is directly related to the energy. All right, and so that's going to be one of the key things that we're going to be quantifying here in a bit. Suffice it to say, we're looking at different wavelengths, different frequencies of light as we move from left to right across this horizontal axis. And then on the vertical axis, we're looking at the rate of electron ejection. And so basically this comes down to looking at the current. Okay, so we're monitoring the current in that little amp meter or whatever you have plugged into that circuit. So what we see is two different lines, a blue line and a red line. The red line corresponds to a lower intensity of light. Okay, so fewer beams of light impacting that metal sample, and the blue one is a higher intensity of light. And so when you're down here at these relatively lower frequencies until about this point here, it doesn't matter whether you have a few rays of light coming in or many rays of light coming in, there's absolutely zero electrons that are being kicked out, right? No current. But once you hit a certain frequency here, there's a threshold that's reached, and we're going to call that the threshold frequency. And after this threshold frequency, then it turns out that it matters, the light intensity. So once you have sufficiently energetic like light rays coming in, then if you have a higher number, the blue line here, then you end up seeing a larger current, right? A larger number of electrons being ejected. And so here's the strange part. The only way that we can really make sense of these results of the photoelectric effect experiments is if we come up with a particle-based explanation, right? In other words, we need to explain this phenomena using the assumption that the light, which we historically thought of as a wave, is actually behaving like a particle. Okay? So the mechanism stays the same. Incoming light is transferring energy to these little electrons, which then shoot out of that metal. Right? But the explanation is fundamentally different from a particle standpoint. Right? In the particle view, what's happening is basically you have these little photons coming in, right? These little packets of light. They're discrete packets, right? You guys might have heard that term before. So we've got little photons that are coming in, and it's only photons with sufficient energy that will cause the ejection of electrons. And that sufficient energy is reached once the incoming photons have a frequency corresponding to this threshold value right here. And so if you don't have individual photons with this sufficient amount of energy to start kicking out the electrons, then it doesn't matter how many of these photons you throw at the metal, you're never going to see an electron coming out. So sometimes students have a hard time understanding this necessity for a particle-like explanation. So I want to take a moment here, a little break, to present a little analogy. Hey, so let's replace this light source, right, which was a lamp. So we had a little light bulb up here. Let's replace that light bulb with me. your professor, your chemistry professor here, right? So remember, this light source was shining, these little beams of light at this metal surface, right? And let's replace these beams of light with tennis balls, right? So we've got a little tennis ball here. Okay, so we've got some tennis balls. And let's replace the metal surface by a piece of drywall. Okay. So drywall hanging on the wall in our lecture hall here. So we've got our metal in the photoelectric effect being replaced with drywall. And now we want to think about what's happening. Okay, now not to feed into any of these stereotypes, but I am not very good at throwing a ball. So if I throw a tennis ball at this drywall, what do you think is going to happen? So of course, it's probably just going to bounce off. So this ball is going to come in, hit the drywall, and then just bounce off the floor. Okay, and it wouldn't matter if I threw one tennis ball, 20 tennis balls, or 100 tennis balls, or 1,000 tennis balls. The chances are, as long as it's a well-constructed lecture hall, I'm never going to be breaking through that drywall. So we'll put drywall remains intact. Okay, I don't work out enough to be able to throw a tennis ball through a drywall. Okay, now let's say I get tired of doing this, but I'm a scientist, so I bring in some equipment in. I say, you know what, I can't actually break that drywall. What if I come in here and I get one of those tennis ball shooters? And yeah, I don't do art very well, but this is my tennis ball cannon. Okay, and I've got my little tennis ball cannon, and now I can supercharge this thing so I can get these tennis balls going really, really fast. And I start shooting tennis balls at the drywall from my tennis ball cannon. Now what's going to happen? Well, of course, now I've got the power to get tennis balls moving fast enough to actually break the drywall. So when these tennis balls impacted, I can actually start breaking the drywall. And so I can then modify this, essentially control the velocity of these tennis balls, and I can monitor and record the velocity at which I crack through the drywall, I break the drywall. And of course, if I turn up the energy beyond that, then I'm going to get into a situation where that tennis ball would come in, hit the drywall, break the drywall, and then you could get little pieces of drywall flying out. And the more energy of the incoming tennis ball, the more energy that will be found in those outgoing little electrons here, or chunks of drywall. And of course, I gave you the analogy here. These chunks of drywall correspond to the little electrons that shoot out of that metal sample in that experiment that illustrates this photoelectric effect. And so this particle-based explanation of this photoelectric effect phenomena was laid out by none other than Einstein himself. So we recall our relationship between speed of light and wavelength and frequency. And we know that the energy of a photon, as we saw in a previous lecture, the energy of a photon is related to both the frequency and the wavelength using this constant. Right, which we introduced before. We said it was Planck's constant, and we'll now see some numerical values and some units for that here shortly. So the energy of a photon related to wavelength and frequency is basically tells us how much energy any sort of incoming photon is going to have. And so Einstein's explanation is then built upon this, and he says, well, light must be comprised of a shower of these particles, these little photons. And each one of those little particles, each one of those photons of light is going to have an energy given by this relationship up here, h nu. Now, the ejection of an electron from the metal depends upon a single photon having sufficient energy to dislodge the electron from the nucleus. Or in my analogy, a tennis ball having sufficient energy to dislodge a piece of drywall from the wall itself. And the energy that's associated with this removal process is basically related then to this threshold frequency. Right? So until you have light of sufficient energy, right, when that's energy, of course, related up here, h E equals h nu, is related to a threshold frequency. And if once you reach this threshold frequency, then you have photons that have sufficient energy to basically start kicking out electrons. So this point, this inflection point really in our little curve here, that inflection point giving us the threshold frequency tells us how tightly electrons are held to the metal that we happen to be observing. And so we call that the binding energy, and we denote that by the Greek letter phi, phi. And so this is a pretty nice explanation. Things start to fall into place. So according to Einstein's prediction, if you have low frequency light, then there's not going to be any electrons ejected, because no single photon has enough energy to reach this threshold frequency, right? But then, of course, if you have photons with a frequency higher than that threshold frequency, then you are certainly going to be able to kick out electrons, and the energy of those kicked out electrons is going to be related to the energy of that incoming photon, h nu, minus how much energy went into actually removing that electron from the metal, right? So our work function here, that basically how tightly those electrons are bound to the metal. So in our analogy, once again, h nu is how much energy I'm putting into a tennis ball that I'm shooting out of my tennis ball cannon, at that drywall. And the phi here is going to be giving us a measure of how strong that drywall is, right? How much energy was required to just break the drywall. And as long as this term, the incoming tennis ball energy, is greater than the energy required to break apart the drywall, then you are in fact going to be breaking drywall, and that positive value is, the resulting energy difference is going to show up as energy in the piece of drywall that's sort of flying away. Now, of course, in an analogy, the tennis ball would still be moving as well, so it wouldn't be perfect. But hopefully you get the idea. So if that's not clear, this would be a good point to go ahead and make a comment in the video. Okay, so where does this leave us? Well, what we've basically shown through these diffraction studies, the double slit experiments, we found that light is a wave. Okay? But the photoelectric effect experiments told us that light is a particle. And so the only way to move forward here is to basically conclude that light is in fact both a wave and a particle. And of course, from a classic standpoint, this makes absolutely no sense. And if you really think about what's going on here and you ask yourself the question, how can something be both a wave and a particle, you're probably not going to be able to come up with a very satisfactory explanation. No one can. And the simple reason being is that we've grown up in a world where we're dealing with nature at a macroscopic level, where we see wave and particle behaviors, two very distinct properties, two very distinct characteristics. But what this experiment is telling us, or these two experiments are telling us, is that when you zoom in on these microscopic, submicroscopic levels to the quantum level, then these sort of common sense notions fundamentally break down, and we need to start thinking about the world in a very different way. Right? And so this is the first instance of that. We need to start thinking of light as simultaneously both a wave and a particle. Now, before we continue with our exploration of quantum theory and applying it to the atoms, I want you guys to take a few minutes and work through a number of practice problems related to the concepts that we've just talked about. And that'll be the subject of the next video.